3.2. All right, to go back to what a function is, it means it passes a vertical line test. So to know if a function has an inverse means that the original graph passes the horizontal line test. So here's an exponential function, and we talked about these in the last couple of sections. If I run a horizontal line over my exponential function, I only hit one time, one time, one time, one time, one time. I constantly only hit one time. Therefore, it does have an inverse. Because the original passes the horizontal line test, the inverse exists. So, if an exponential has an inverse, what's the inverse? And that's what we're going to start talking about here. The inverse is called a logarithmic, but log function. And what it says is if I have an exponential, I have a log. All right? And we talked about these last year in 3.4a. And basically it says whatever the base is, kicks up the other side. So a kicks up the y, and then the log word goes away, leaving the x. And that's how we switch from exponential form to logarithmic form. So here, log base 2 of 32, and that's how you read it. Log base 2 of 32. If I'm going to switch this, I would say, like, I don't know what that value is. So 2 kicks up, the base kicks up the other side, equal to, the log word goes away, the number. 2 to the x is 32. Well, you should know that 2 to the x is 32 is 5, because 2 to the 5th power is what is going to give you 32. So basically, when we're looking at our logs, we're asking what power on the base gives me that number. What power on 3 gives me 27? And hopefully we know that that's 3 cubed. What power on 4 gives me a 2? And if you're unsure, you can look at it. What power on 4 is going to give me a 2? Well, the only way 4 can become 2 is if I square root it. So what is the square root? What exponent allows for a square root? That's 1/2. What power on 10? What power on 10 allows for 1 over 100? Well, in order for that to become a fraction, it has to be negative, because it's going to have to cross the line and change the sign. And how does 10 become 100? 2. What power on 3 is going to give me a 1? The only thing that gives me a 1 is a 0. What power on 2 is going to give me a 2? Well, the only way you get yourself is if it's a 1. All right. On our calculator and in our normal conversations, the log is always in base of 10. If it's not in base of 10, it's going to be written log base 3, log base 4, log base 2. It's going to be written. Generally, if it is in log base 10, you would not see the number. Now, we did it here because we're just looking at examples. But generally, if you just see no base number written, that implies a base of 10, because that's our general default. All right, on page 2, since log base a of x is the inverse of a of x, the domain of the first is the range of the second. And then, I don't know why this line is here. So log base a of x is only defined if x is positive. That is a key part. This must be positive. It cannot be anything else. It must be positive. All right, so use the calculator to evaluate log base 10 of 10, 2 log base 10 of 3.5, and log base 10 of negative 2. Now, as I told you, our calculator in our normal wording and stuff is already in base of 10. So when you're typing in the log, all you have to do is actually hit log and then 10. And the base of 10 is already in my calculator. So 10 of 10 is 1. 2 log, base 10 is already there. 3.5, 1.088. Again, 3 decimal places is fine, round appropriately. And log of negative 2, we get an error, and the reason for that is you cannot have negatives, so no solution. All right, log base a of 1 is 0. Any base to the 1, because the only exponent I can put on the base to get 1 is 0. This is that whole transformation. The base kicks up the other side, leaving that number. Because the base kicks up the other side, leaving that number. This is called the inverse property. If I have a log base of a number, it equals the exponent. And the reason for that is basically those are going to cancel out. And the same thing happens if I have exponent, a base of an exponent is the base of the same. All that stuff cancels out, leaving just the x. And if I have the same log and base, well then their number parts have to be equal. So that's called the one-to-one property. So the inverse property and one-to-one property. So we're going to solve each of these. Here we have the log base is the same, so log base. So x must be 3, and that's because of the one-to-one property. Here I have 4 of 4 is x because of property number 2. That says if my number, my base gets to kick up. So 4 to the x is 4. So 4 to the x equals 4 to the 1. The word log goes away, so x must be 1. Letter C here, we have 4 of x and log 4 of 64. This we get to kind of rewrite so that we're going to get the inverse property. So we're going to have log 4 of 4x is log 4, and then 64 is really 4 cubed. So log 4 means 4x is 4 cubed, so x is cubed. 3 of x equals x. If the base of the log and the base of the exponent are the same, it leaves the exponent. And that's from property number 3 up there, which is the inverse property. And the same thing happens on letter E here. If the base of the exponent and the base of the log are the same, they go away, leaving x. So same rule applies to both properties. All right, to sketch the graph of a log, we're going to use the fact that the graphs are inverses, which means if they are inverses, they reflect over the line y equals x. And we got this from couple chapters ago that if something's an inverse of each other, it reflects over the y equals x. So if I look at my equation here, here's f of x. See x and 2x, so that's how I know it's my letter A here. It tells me my points. I get -2 is 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and I get this F line. Again, I know that my asymptote is the x-axis for that one. I have an asymptote of the x-axis. All right, and these were my x values, and these are my y values. All right, well, that's my exponential form. So if I'm going to do the inverse, which is log form, and that's what it is, a log is the inverse of an exponential, well, that means everything is going to change. That means my asymptote is the y-axis. And I'm going to be reflecting, the whole thing is going to reflect over y equals x. My y values of the original exponential become my x values, and the x values become now my y values. That's what it means to be an inverse of each other. So 1/4 is going to be -2. Negative, or 1/2 is going to be -1. 0 is 1. 2 is my x value. 1 is my y value. 4, 2. 8, 3. So what's happening here is that they are reflections of each other over the y equals x. And every x value here became a y value, and every y value became the x value. That's what it means for these to be inverses of each other. We're not using the calculator at this point. You need to understand what this is by hand. So on this next page where it talks about the basic characteristics of our log function, it's the inverse of what our basic characteristics of the exponential function is. We are still going to do things with the logs that we've been doing with our exponentials, with all of our polynomials, and that's going to be transformations. Our transformations, so here's our general, y equals log base 10, because that's our general, x minus h plus k, and it maintains the exact same principle. H's are going to move me left and right, opposite sign. K's are going to move me up and down of the same sign. So when I look at my examples down here, I know my original graph is going to move or shift 1 to the right, 1 opposite sign. This is outside of the parentheses, so it means it's my k, means it's going to go 5 up, same sign, positive. The negative function is going to reflect over the x-axis, and the negative x means we're reflecting over the y-axis. So all of our transformations are staying consistent and staying the same, just like we've been doing on every single one of our graphs. The natural log function with base e, instead of saying log base e of x, because e is so instead of saying log base e of x, because e is its unique property, it's our natural number, our natural base, we use ln of x. ln, and it's literally read as L, the letter L, N like the letter N, means that the base is e but we do not write it. See how log of e becomes natural log of e, but we do not write the base of e in here. We don't write that e in there. Just like we don't write a 10 in a log log. We don't write the base of 10. In an ln log, we don't write the base of e. So it's already implied. ln is always base of e. We have an ln button. So when you're asked to find the natural log of something, you use ln. ln of 2. Make it 3 decimal places. Make sure to round appropriately. Do B, C, and D quickly on your own. Pause the video. You should have come up with 0.91632 and no solution. Again, this part cannot be negative. It has to be positive. The properties of our natural log are exactly the same as the properties of our logs. So it doesn't matter if it's ln or log. If I'm going to be 1, I'm always going to be 0, because the only way a base can be 0 is if my answer is 1. So anything to the 0 is 1. E to the e, well, that's the only way I can get it. If the base of the log and the base of the exponent are the same, it cancels. If the base of the exponent and the base of the log are the same, it cancels. If ln and ln are the like, then so must be their parts. So the rules for logs, LOGs, are the exact same as our rules for ln. So we're going to use the properties here. Here we're going to get the natural log of 1 over e is the same as e to the negative 1. Well, again, we don't write our base of e, but when the base and the number are the same, all goes away for negative 1. Again, the base is e, goes away for 2. The base is e, cancels for 0. Base of e goes away for 2. Alright, because we know that our parts cannot be negative, to find the domain, you set the inside greater than 0, because it can't be 0 and it can't be negative. So therefore, it has to be greater than 0. So x is greater than 2 means interval notation 2 to infinity. Here I have 2 minus x is greater than 0. Negative x is greater than negative 2. So x is less than 2. Well, that's negative infinity to 2. Again, interval notation. X squared has to be greater than 0. Remember, when we square, we have to switch our signs. We have to account for the positive and the negative. So we would say we're everything except 0, which in interval notation means negative infinity to 0 and 0 to infinity. It cannot be negative infinity to positive infinity, because at 0 it breaks. So this cannot happen. You must write it as a broken interval, because it does not touch at 0. So you cannot have it included in your solution. Alright, then we have our last page. If you're given a function, can you plug in some information? So if t is 0, 75 minus 6, natural log, 0 plus 1. Should be able to put that into your calculator. 2 months. So again, we're just going to replace our time with 2. Put it in your calculator. Come up with a solution. What was the score at the end of 6 months? So replace your time with 6. and plug it in your calculator. So really on that last page is just, can you substitute, can you put in the pieces where you need to based on the equation that's given, can you use your calculator? And that concludes 3.2.